Hello, everybody. My name is Julian Reed.
And I'm Ari Maharaj.
Today, we wanted to give you some breakdown for our summer project here. Ari's going to handle the background, the objective of the project, and the overall significance to all the work that we've done. He'll give you some insight into his experience modeling, prototyping, and finally producing some vital components for our setup. And then I'll take over and I'll walk you through a typical day in the lab and give you an oversight of our development, deployment process, and technical challenges that we experienced. Then I will finish up with the conclusions. So without further ado, I'm going to hand it over to Ari. He's going to run us over the background.
Thank you, Julian. So the project we were given for the summer was to evaluate a small-scale vision language model, or VLM for short, and vision language action, VLA for short. We were to deploy this evaluation on a standard OpenARM 101 or SO 101. And along with the SO 101, we were to use an Intel RealSense RGB and depth camera for spatial perception and 3D control. And alongside all of this, we had a data collection interface that was designed to capture synchronized video and SO 101 movements during the live demos and recording progress sessions. But why did we use this small scale testing of evaluation instead of deploying it on the actual robots that would be using this? So the purpose of the small scale testing was for its exchangeability. If a servo motor were to burn out or malfunction on the SO101 robots, instead of having to replace a $1,500 motor on the larger robots, we could just buy a $30 motor on Amazon and replace it the next day. The same applies to their motherboards. Not only is the replaceability a good thing to keep in mind, but the ease of adjusting a camera angle with just a few screws in it is much easier than switching around a whole camera rig. But what is the whole point of this? Why use a small robot? The purpose of this is to determine the reliability of a small scale VLA/VLM pipeline. If we can apply the pipelines to the smaller robots, then we can figure out ways how to scale them up to larger robots, such as the Franca Amica. Once we can get the pipeline worked out and functional, then we can continue to build off that pipeline and implement new attachments, such as the real hand, to work in tandem. As for my experience in modeling, prototyping, and final products, I would have to say that was my favorite part of the whole project. I enjoyed working with CAD and figuring out how pieces would work with each other. And one of those pieces that was more memorable for me was the Intel camera mount. I had to figure out how to allow for adjustments of the camera angle to be made while still being fastened securely. I had some outside input, but the final design was to have a protruding nub that the camera would be able to rest atop of while having a screw hole come out from the other side of the stand to be able to secure it. It took a few iterations as I had to get the screw hole length to be just enough to make it so that the camera would be securely mounted. And I also messed up with a few of the dimensions on the first one, but I was able to fix that. And in the end, I had a final product and we used it to gather good video data for the models to be trained off of.
So with all that context out of the way, I kind of move us over to the next section here in the middle, which is the results. So you're going to see four pictures here, and each is really emblematic of different stages of our development. So first off, you can see up here we have our primary state, which is just the standard workspace. Now, this is really interesting because it crosses over with our technical challenges here. One of the biggest issues that we had was just getting uh, over that first hurdle of getting everything set up. The big delay came from we were really determined on having everything mobile. We wanted to be able to take the robot with us home and have our workspace, outside of school so we didn't have to come in as often. And we were kind of just determined to have that flexibility. The root problem here is that the camera that we're using, the Intel RealSense, does not like to talk to Apple infrastructure. This is down to multiple factors, but really the simple part of it is that Apple's very selective about who they let use their drivers, and they don't like to work with Intel anymore. So there's some workarounds for this, and that's why we spent so long on trying to get it to work on my computer. Um, you can run basically admin commands to bypass some of these restrictions, give it root access to your machine, but you're still going to have trial and error. Eventually, we did get it working, which is, I mean, it proves, it's possible. But the resulting data file was over 170 gigabytes, and this was probably, I want to say, about 150 episodes of data. Um, and I'll explain to you what episodes are here in a minute. But eventually, after fighting with it for about, I want to say about probably half of the time that we have been in here, so like 4 to 5 weeks, we just bit the bullet and we set up our nice little workspace here. And you can see we have a, desktop computer, and that's one of the university machines. So that's our linchpin for the entire setup. We do all of our data collection, all of our training on here. So I said the word episode earlier, and I'm gonna explain to you what that is in a minute. So we're gonna move on here to the second image, and already mentioned earlier, talking about visual language models. And one thing about visual language models is that consistency is really key. That's why having a well-defined workspace is really vital. Something as simple as a different camera angle can change how well or how poorly that your model is going to perform. This is especially true with what we've been using to train the robot, which is this model or this backend called Action Chunk Transformer. It's good in the fact that it's precise, right? So if you have a very clearly blocked task, like for example, something working in a factory that just has to screw in the same screw over and over again all day, it's gonna do really well. It knows what it's doing, but the problem with ACT is that it's not very smart. Um, so that's where consistency comes in to play. We have other backends that we can use. One's called small VLA. Um, the small comes from the fact that it uses not a lot of parameters in its training, and VLA is for vision language action. And this is one that is actually, it functions in the same way that generative AI does. So it's able to interpret written language prompts and then perform that action based off of the data that's been given to be trained on. So after some messing around, we got our setup and everything. There's still some room for improvement. We needed some overhead lighting. We've had some issues with shadows, and that will help to up the consistency that we get between episodes. So explaining what an episode is, I haven't still not done that. I'm going to do that now. The data that we collect is collected in sessions that we call episodes. So in every episode, you're going to be performing the same action. You're going to be, for example, in this picture, we have it picking up a block and placing it. You can have introduce some variation, but depending on the model, you want it to be fairly consistent. Um, During the symposium, we're going to be having the robot pick up a cube and place it into a tray. And while we collect the data, what I do is I just go through and I put the block in a spot, and then I do 15 to 20 repetitions of that action. And then I move the block to a different spot, and then I do 15 to 20 episodes of that action in that spot. So basically, for every spot that you could place the block within this certain parameters, I will have data, and the model will be trained off that data, so it will be able to perform it. An episode is just a clean cut, start to finish, do the task, right? And you can't just have one and repeat it, 100 times because there's going to be some level of variation in real life. So you want to do the action manually, right? Because if you want our robot to do something, you have to show him how to do it. He's not just going to be able to do it. on its own. So on the third image here, we run it through our neural network. I've already kind of explained how that works. There's different models that we train it with. I've been using Action Chunk Transformer or ACT just because I like how precise it is, but the problem with that is the fact that it's not very smart, like I said earlier. So you can't introduce a lot of variation into it. So we run it through the training and then it's done after about an hour and a half, 2 hours, and we just hit play. And within 30 seconds, usually, depending on, whether or not he feels like doing the task, Jimmy, our robot, will pick up and place the block where we want it to go. So it's a pretty simple process once you have everything set up. You just repeat everything and 100 200 times, and eventually your robot will be able to do what it needs to do. um Coming over here to the technical challenges, this is where things get hard. So this image says gripper motor failures, but that doesn't really define really the real issue here. The problem with this is that it's not the gripper motor itself failing, it's failing to report its current position to the backend software that we're using. So that causes a cascade failure because it doesn't read, and then the next motor in line doesn't read, et cetera, et cetera. And it just causes the whole thing to crash and essentially roll over. So, um, and then you have to restart your data collection because it ends the session. So, luckily, the developers of Lay Robot over at Hugging Face have graciously given us tools to mesh our data sets together. So sometimes when I'm collecting data, this is one of my challenges is that I'll get one episode before we get a cascade failure, and then I have to end the session and just upload that data set of one episode and then come back and stick it, essentially glue everything together into one long data set. So that's just kind of an annoyance. It takes time out of your day. You have to re-enter all your parameters and everything. It just takes time. Another issue that I noticed that we were having is that one of the parts of the project was to get a basically a visual language model going, and I'm going to zoom in here if I can, if it'll let me. Never mind. You can see these little green squares. We basically have a model running that is, able to recognize these cubes that I'm holding in my hands. The problem with this was that it was not able to see it when it was up against our old grid background. So we had to change the background out and re-record a lot of data with that solid black background because it was just introducing too much content or what word am I looking for? It was introducing too much just noise into the data and it was causing things to mess up. And we were able to catch that with the perception model. Again, I brushed on this earlier, but the biggest hurdle was really just accepting the fact that we can't get the real sense to work with a MacBook. Um, I even tried to get a virtual machine running on my MacBook running Linux, and I still could not get it to work. I had the whole file, brought it over from GitHub into my virtual machine. It still just would not work. It's just hard, just a no. It's not even worth bothering with. You really need a Windows or a Linux machine, and you can't bypass Mac hardware with a virtual machine, unfortunately. So you're still gonna have those issues there. So coming around to the conclusions, the question that we want to answer is, can the SO 101 reliably serve as a low-cost testbed for language-driven pipelines? I would say yes, with some caveats. We really need more time to work on this project, and thankfully, thanks to Dr. Zhang, we're going to get it. We're going to be working with her in the fall as well. But as we've seen, I mean, from my experience, is that yes, it is a decent pipeline. It's there's some hiccups, especially with the motors failing constantly and giving you that cascade failure. There's some lagging, but that might just be a hardware issue with the PC stack that we're using. I would assume that is the problem that we're having because we have so much plugged into the computer right now. I mean, there's three different cameras, the two robot arms. There's just a lot going on, and then it's running the back end and the front end, and everything's talking to each other. I'm assuming it's just dropping communication. It's just lagging. So I would say that is a bottleneck that we need to address in the future if we want this to really be the best that it can be. We probably should get, a better motherboard or something just to fully overcome some of these key bottlenecks that we're facing. But as it stands right now, with some caveats, yes, it is a viable low cost test bed for developing these models, and I hope to be around to finally see something like this deployed on the Franco robot we have in the laboratory. So thank you for your time. I hope this wasn't too long of a presentation. I hope it was interesting. I hope you kind of came away with an understanding of our project. And feel free to ask me questions at the symposium on Thursday. I can give you a more in-depth explanation on exactly what's happening, and you'll be able to see the robot, mess around with it. Yeah, thank you very much. Ari,
Thank
you
you.
want to say anything, Ari?
Thank you. Good luck. Have fun, everyone.